Okay, hello everyone. You should be hearing me now, and if you do hear me, please give me a thumbs up in Gathertown so I know that you are indeed hearing me. Excellent. I see several of you raising your thumbs, so thank you for that. Thanks for confirming. So what we're going to do today is continue with rotation and essentially um, closing or ending the chapter on fixed axis rotation, where the axis is fixed naturally. We talked a little bit at the end of Monday's class about work energy theorem. We introduced the expression for work, and so we're gonna come back to that just very briefly, and then we're going to go into chapter 11 and start talking about angular momentum. And actually, the first two sections, or the first section, which includes two topics of chapter 11, is actually not as much about angular momentum, but about solving problems of fixed axis rotation and moving axis rotation, as you'll see, but fixed axis direction. So it will actually be a good example and a good application of the chapter 10 material. So let's start with finding my cursor. Okay. So let's start with fixed axis rotation and work energy theorem. So what we introduced last time was the expression for work in rotational coordinates. So we essentially are looking at an object here that is rotating from one position A to a position B, and it's rotating around a fixed axis at the origin here. It's rotating over an angle d theta, and it's rotating under the influence of a force F, which has a radial component and a tangential component. So what we used is we went through a little bit of a description, a little bit of a derivation to calculate the expression for work. And what we found is the following expression, that the work in rotational coordinates, the work, which is W, is the integral over the total torque times the dot product with d theta, and that integrated between points A and point B. So essentially, the total torque, which in this case here will be just a single torque due to the perpendicular component of the force times the lever arm, so that torque multiplied with d theta and then summed over all of the d thetas, that will give us the amount of work. So this is expressed here as an integral from a point A to a point B. Of course, if our torque is constant, if the torque is constant, then the integral simplifies. Then W becomes the integral, well, W becomes the torque times the integral from A to B of d theta, and that's just the torque times d theta from A to B. And that's, of course, one of the simplified versions that we'll often encounter. The actual complicated integral is not going to be as relevant for this particular course, but of course in general it's the expression to use. So where do we use the work now? Well, this is the work to go from A to B. The work to go from A to B, just to be explicit about it here. So if that's the work to go from A to B, the work energy theorem says, just like in the case of linear motion or translational motion, that that work to go from A to B will have to be equal to the change in kinetic energy. If the work is positive, if in other words the torque is in such a direction that it adds, that it is in the same direction as the change in the angle, the torque is in other words moving or the torque is in the direction that the angle changes. If that's the case, then we are putting additional energy into the system. And if that work is positive, then the kinetic energy at the end point B will be larger than the kinetic energy at the starting point A. So if we combine that now with the previous expression, we have that this is the integral from A to B of the total torque d theta. So that's now what we're going to be able to use to calculate the change in kinetic energy based on the torque only. And from that change in kinetic energy, we'll be able to calculate, of course, the parameters that go into this kinetic energy. If the kinetic energy in our case is 1/2, well, it is in our case 1/2 I times omega squared. If we know I, we can calculate omega, for example. So let's actually apply that to exactly this problem. So just to recap, the problem-solving strategy will be then to first identify the forces and calculate the torques, then calculate the work done for the given rotation, and then apply the work energy theorem to calculate the changing rotational kinetic energy, and then derive the omega. So we're going to apply that to a particular problem of this pulley here. So this is a pulley hanging from the ceiling. There's a rope that is over the pulley, and or a string, I guess. It's a light duty pulley with a string. So this string is pulled with a force of 50 newtons. The pulley itself has a radius of 0.1 meters, and the moment of inertia is 2.5 10 to the 3 kilogram meter squared. So you could actually calculate what the radius of that pulley is. You could calculate the mass of the pulley from those two pieces of information, assuming a uniform disk. And the total distance over which we pull that pulley at a force of 50 newtons is 1 meter. So there's 1 meter of string that is unwound. So the question now is, if we start from rest, if this pulley is not moving initially, and after we've unwound 1 meter of string at a force of 50 newtons, what is going to be the rotational velocity, the angular velocity for the pulley? So let's see if we can solve that. So we're going to calculate. We're going to follow that problem-solving strategy, right? So for the pulley system, we're going to start by calculating the torques. So if we want to calculate the torque in this case will be the force times the distance to the axis of rotation. So the torque will be the force times the radius, F times R. So that's F times R, that's the torque. And the other thing we need to get to our work is the change in angle. As the torque is constant, because the torque is constant, we can use the fact that the work to go from A to B is going to be torque times the change in angle. So to get to the change in angle, we're going to use the distance that or the length of the string that is unwound, which we'll call little d, and so the distance d that is unwound here on a disk that has a radius r, that will correspond to an angle that is rotated over, that is d over r, right? So if we put that all together, that means that the work to go from A to B, to go from rest to motion after having unwound 1 meter of string, that will be F times R times d theta. That's d over r, and that's just F times d, right? So that's the work that's done over the course of this problem. And we can of course plug in the numbers. So in this case we have that F is 50 newtons, and the distance is 1 meter. So we have 50 newton times 1.0 meters. So that's going to be a total work of 50 Newton meters. Okay. Now we could of course have done this this more quickly. We don't need rotational motion to do this, because we know that if we pull with a constant force, and there's a displacement of this string over 1 meter, we just multiply F by D, and we get the same answer, right? We could have immediately written down the work here, F times D. There's no difference whether this is a rotational motion or not. We don't have to use tau times d theta, but we can use tau times d theta and obtain the result that way. And in particular, if we have multiple torques, then of course adding all the torques together and then using d theta might be easier than writing a different component for a different force and different distances in different directions. Okay, so now that we have the work that's equal to F times D, we can get to the change in kinetic energy, right? So just to answer in the chat, there's a question: how do we get to this? Well, if this is the angle, so let's write it the other way around. The circumference of a circle, which shall not surprise you, of a circle is 2 pi r, right? So that means an angle of 2 pi d theta and a radius r corresponds to a length, that is the circumference, that is d theta times r. And so in general, the arc length is r times delta theta. And so in this case, our arc length is actually d, so we can get to that d theta as the arc length d over the radius r. So that's the reason why we get to d over r in that case. So back to our work energy theorem. So now work from A to B, which is F times d, that is equal to the change in kinetic energy, Kb minus Ka. But we know that the kinetic energy at A is 0. The kinetic energy at B is 1/2 I omega squared, because at that point the disk and the pulley is rotating. So we now have an equation that we can use to solve for omega, right? F times d is 1/2 I omega squared. So that means that omega will have to be 2 Fd over I with a square root. And if we plug in the numbers, we'll find that this is 2 times F times d, so that's 2 times 50 Newton meters over a moment of inertia, that's 2.5 10 to the 6th. Sorry, what was it? 10 to the 3rd, right? 10 to the 3rd kilogram meter squared with a square root. And if you plug in the numbers and you calculate that expression, you'll find that this is 200 radians per second. So that's our final omega. In some sense, we should maybe, we can add b here, because omega a is equal to 0. So what happens is, as we pull with 50 newtons, the string unwinds over a distance of 1 meter, and starting from rest, because we pull, the pulley starts rotating until after that 1 meter of string is unwound, it is rotating at an angular velocity of 200 radians per second. So the other thing we introduced last time was power, right? Power, which is P is dW dt, so it's work done per unit time. So we can apply that here too. Let's imagine if the pulley is pulled and then we transfer that or we pull the string by 1 meter in 20 seconds, if delta t is 20 seconds, what will be the power then? So take a second to think about that. How would you calculate the power based on the information you have now? So one way to do it would be to calculate just the work over delta t, right? So that's going to be the work that we calculated, which is or 50 Newton meters. So P is 50 Newton meters over 20 seconds, or in other words, that's 2.5 watt, right? Now there's another expression that we introduced last class on Monday, and that is that. Gosh. So the other expression that we introduced is that the power is equal to the torque times omega. So the power is equal to torque times omega. So one thing you might think of doing here is, well, let's see what we get if we multiply the torque times omega. So that is going to be or 200 radians per second times the torque, which is F times R. So that's 50 newtons times 0.1 meters for R times 200 radians per second. And we can multiply all that together. And I guess I don't need to tell you that this is not going to be equal to 2.5 watt, right? So what's going on in this second expression that this doesn't seem to work, even though we've calculated last time that P is also able to be written as the torque times omega. So who can tell me what the problem is here? Why this doesn't work or doesn't seem to work? Anyone in the chat? So the units are fine, right? It's newtons times meter over second. Radians is not really a unit. Radians is essentially what we use to keep track of angles. But there's also so that doesn't really count as a unit. So I do see some idea of the reason, and that's that the torque is indeed not constant. Excuse me, the torque is constant. Omega isn't constant, right? So what we have is actually omega increases from 0 to an omega of 200 radians per second. So the omega that we plug in here in this expression is not constant. So this expression, P is tau times omega, that is the instantaneous power. Whereas what we actually calculated here, this is the average power. And so what that means is that as omega increases, even though the torque remains constant, the power will increase, but such that the average power is actually the average power is going to be smaller, of course, than the power at the end point when the omega is at its highest value. Okay. Any questions about this problem of the pulley? I'll just push and pull this up again. Okay. Let's see, where did it all go? There it is. So if there's no questions, then we'll actually move on to angular momentum. Actually, let me just show you this comparison again. Now that we have completed this whole chapter, also about work and energy, we can look back and look at all of the different translational and rotational variables and kinematics and dynamics, and look at the parallels between them. So we've of course looked at this before, but it doesn't hurt to put this up again. So the angle behaves like the position, the angular velocity behaves like the tangential velocity, and the angular acceleration behaves like the tangential acceleration. And then if we okay, give me a second here, the dogs are going crazy. Okay, I'm back. So the other formulas we introduced were the kinematics formulas, which are also very similar. Translational kinematics, calculating the position based on the average velocity, calculating the angle based on the average angular velocity. And we have angular velocity and velocity in terms of angular acceleration and acceleration. We have this formula, position in terms of time and acceleration and velocity, and velocity in terms of acceleration and change in position or change in angle. So all of those are also very similar. And then these are now the ones that we can complete. That's our power here, the last one that we calculated, and the work, which are as you can see now also very similar. So these are a couple of tables that are good to keep in mind, and maybe even to keep in as a tab in your browser when we do the exam, because they'll be able to give you a shortcut to some of these formulas. Okay. So one question is, for Friday's homework, do we use the radian setting on the calculators? Probably. In most cases, omega will be, or almost all cases, omega will be in radians per second, unless of course it's specified as RPM, or if it's specified as angles, specifically as degrees per minute or something. So of course you have to use the right unit conversion, but omega will typically be in radians per second. That's the SI unit. Okay, on to chapter 11. So chapter 11, the first section there is rolling without slipping. That's an example now that combines some of this rotational and some of the angular, some of the translational dynamics. In particular, what it does is it's looking at a system that's rotating, like this bicycle wheel, and at the same time it's moving forward, and it is moving, in this case, without slipping. So, well, you know what rolling without slipping is. What happens is there's no slipping at the point, to the contact point with the ground. So we're going to treat that in a little bit of detail because it's a good example of combining angular and translational motion. And the next step is we're going to turn it into a discussion of angular momentum. So let's look at this schematically. Let's first look at we can write down the forces on the wheel, but we're actually going to look at that in a little bit more detail in a second. So let's skip to panel B here, which is looking at the velocity of the center of mass for a rotating disk. So we have our angular variables, or angular velocity, which is the velocity with which, or the angular velocity with which the wheel is rotating around its axis. We have an angular acceleration. We have a linear velocity and a linear acceleration, which is written here for the center of mass. And we have one point here. That's the contact point with the ground. This is where the rolling without slipping happens. the rolling without slipping means that this contact point is fixed. If we think of this contact point as being located on the wheel, that means that the combination of the center of mass velocity and the rotational velocity, the tangential velocity due to rotation in the center of mass frame, that combined velocity will have to be equal to the velocity of the ground, or in other words, that will have to be equal to 0, right? So we're going to start by writing down the velocity of this point P, starting from the center of mass velocity and the angular velocity. So if we write that down, let me maybe just erase this stuff or put it somewhere else. Let's put that over here. So then the new page for rolling without slipping. So rolling without slipping requires that we calculate that velocity, requires that we calculate the velocity of the point P. So that will be the rotational velocity. And the rotational velocity is shown here in this third panel. So that's the velocity going in the minus x direction. And it has a magnitude of r times omega. That's the tangential velocity due to rotational motion. So that's Vt of point P. And then to that we'll have to add the center of mass velocity, which is in the positive, which is in the positive x direction. So that's plus V center of mass. So that will be the total velocity of the point P, and we can write this as minus r omega in the x direction. So let me just write this as Vp. It's minus r omega in the x direction plus V center of mass in the x direction, where V center of mass is now a scalar quantity. So that is our expression for the velocity at point P. No slipping will now mean that Vp is equal to 0. So if there's no slipping, then that will be equal to 0, and that means that minus r omega plus Vcm in the x direction will be equal to 0. And that in turn means that we can write Vcm as r times omega. Of course, that's of course not really a surprise that the center of mass of the wheel has to move at r times omega in the case of no slipping. But this now formalizes that. So the center of mass velocity is r times omega. Of course, we can from that derive that the center of mass acceleration will have to be the time derivative ddt of r times omega. So r times the time derivative of omega, so r times alpha. The angular velocity, the angular acceleration times r will have to be equal to the translational acceleration. And the other thing we can do is look at the distance traveled. That's, instead of taking the derivative, we take what some of you like to call the antiderivative, the integral over dt. So that gives us the distance traveled by the center of mass. That's the integral of Vcm dt, or the integral of r omega dt, or r times the integral of omega dt, and that is r times d theta, or r times theta, the angle that is traveled. And of course this gives us that if we apply the first time derivative to it. The important one is going to be this acceleration one. That's the one that we're going to use next. So just as a reminder, we calculate the velocity of the point P starting from the center of mass, which is the the velocity of the center of mass, that's where the axis of rotation is, plus then the relative velocity of point P because of the rotation around that axis. And that velocity of point P, when there's no slipping, has to be equal to 0. So this is incidentally, this is the same derivation I did earlier. That's starting from arc length, going to distance traveled, or going to the length of the string in the case of the pulley problem. So that might be a useful slide as well. Okay, so now let's make it a little bit more complicated. What we're going to do is immediately apply this to an inclined plane. So we're going to use, we're going to take an object that is rolling without slipping down a slope or down an inclined plane with an angle theta with respect to the horizontal. So what we're going to do is we're going to determine what the acceleration is of the center of mass. So what we want to calculate is the acceleration with which the object is rolling down the inclined plane. So the translational acceleration. Of course, we're also going to need to calculate the rotational acceleration. But ultimately, what we are after is how fast does this roll down the inclined plane, and how do we get that from or all the forces involved. You essentially writing this only in terms of mass, g, the angle, and the moment of inertia of the object that's rolling down. Okay. So the way we approach this is we're going to write down a couple of things. We're going to write down our free body diagram in an axis coordinate system that has x and y in this direction. We're going to write down our angular motion in terms of the torque around the center of rotation. And then we're going to relate the angular acceleration and the translational acceleration in the x direction because we're rolling without slipping. So that will allow us to relate that exactly with this equation that I've, or with this relation here that I've put in a box. So, so let's start with that. So inclined plane. So we have our free body diagram and Newton's second law in translational coordinates. So that's going to be in the x and the y direction. So in the x direction, we have that, so x and y. In the x direction, here we have that mg times sine theta minus the force of static friction, which has to be there, of course, because of the fact that there's no slipping. So there must be some friction there. So we'll have that mg times sine theta minus the force of static friction has to be equal to mass times translational center of mass acceleration, right? So just going back to the figure, you can see that mg times sine theta minus fs has to be the acceleration downwards into the x direction. So now in the y direction, we have the normal force that's going in the plus y direction and minus mg cosine theta that's going into the minus y direction. So that's n minus mg cosine theta. And the acceleration in the y direction will have to be equal to 0 because all of the acceleration is along the x direction. None of the acceleration is along the y direction. So those are the first two equations. That's what we get from our Newton's second law in translational coordinates. Now we're going to look at torque, and we're going to use Newton's second law in rotational coordinates. So in rotational coordinates, we can calculate the torque. So we're going to use the same free body diagram, and we're going to calculate all of the torques around the center here. Now we have the normal force, and the normal force is pointing right through the center. So that's going to be a 0 torque. mg times sine theta applies at the center of mass and is therefore also going to have a 0 torque. Minus mg cosine theta applies at the center of mass and is also going to have a 0 torque. The only non-zero torque is this friction. And that makes sense. The thing that makes this cylinder or this ball rotate is going to be the friction. That's the force that that causes the torque. And since that's the force that causes the torque, that will be the one that causes the angular acceleration. So the net torque will be that force of friction times the distance at which it applies, which is r. So the torque is Fs times r, and that will be equal to, now it's not mass times translational acceleration, but it's moment of inertia times, so moment of inertia around the center of mass times angular acceleration. Okay. So now we have our translational coordinates, rotational coordinates. Now we just need to combine them together. And that's what we use this formula in the box for. So alpha times r is ACM. So that's the connection due to rolling without slipping. So if we do rolling without slipping, that's the equation that applies, and that allows us to connect this equation with that equation. And of course, there's other things we're going to calculate as well. We're going to connect Fs with Fs here, but we can now solve that system of 4 equations: 1, 2, 3, 4. So let's solve first for Fs, for the force of friction. The force of friction is going to be, from this equation, is going to be ICM alpha over r. Okay. If we add the second equation, this is ICM, and I guess I should have used a little r here to be consistent. That's the same little r. So that's going to be ACM over r squared, because alpha is ACM over r. So now that we have Fs, we're going to plug this into the equation for x, so that we have, we have mg sine theta minus Fs, which is ICM ACM over r squared. That must be equal to mass times ACM. And now, of course, we can solve for ACM. ACM is going to be equal to mg sine theta over the sum of these two parts. So that's going to be m plus ICM over r squared. Okay, so there we have it. We have calculated the translational acceleration of the object rolling down the inclined plane in terms of mg, theta, and initial and moment of inertia. Notice that if ICM is equal to 0, which is essentially just a massless particle rolling down the inclined plane, then we just get ACM is g times sine theta, which is the expression that we actually obtained for just sliding down an inclined plane, because there's no difference between an extensionless object rolling and an extensionless object sliding frictionlessly. So that is something that we recover here. We also see that we find a smaller value due to this moment of inertia. So the acceleration will be smaller. And part of that is, of course, that it takes energy that needs to be added to the rotational kinetic energy of the object, in addition to the translational kinetic energy. Previously, in just sliding down an inclined plane, the only thing we needed to do was give kinetic energy to the translational motion, not to the rotational motion. But now we have to give energy to the rotational motion as well. Okay, so one last thing we need to do is now check that there's indeed no slipping. So if there's no slipping, that means that Fs must be less than or equal to mu s times n. So that means there must be a condition for mu s for which that is satisfied. And this is where we're going to use the y equation, which says that the normal force is mg times cosine theta. So this will have to be equal to mu s times mg cosine theta. So we can turn this now around using our question or expression for the static force of friction. We can plug in the acceleration here, and we can find an expression that mu s will have to be greater than the tangent of theta over mr squared over I cm plus 1. So there's going to be a minimum coefficient of friction that has to be provided before we will indeed be able to be in the no slipping case, and indeed the static force of friction can prevent the slipping from happening. So that's what I wanted to do for today, and we'll continue with that in the next lecture on Friday, when we actually will allow some slipping. So if we allow slipping, then of course we won't use static friction, but in the case of slipping, we're going to use kinetic friction. Other than that, it's all going to be very similar. The difference is going to be that the force of friction won't be as large as it needs to be, but it will be given in terms of the normal force. So we'll pick that up on Friday. Okay, then let's pick this up on Friday. And for those of you who have final exams, good luck with them between now and then. And talk to you on Friday.